Well, yes, we are back. Okay. Thank you guys for coming back. Um, yes, Paula, we are back. Good morning, Catherine, Cassandra. We're back at it. Okay. So I'm kind of curious to see just how many people we actually lose. We shouldn't lose anybody. Okay. There's still lecture. We just wanted to start clean with the next distribution. Okay. The next kind of topic. So that's what I want to make sure we do. And it looks like we lost about half those students. So hopefully they come back. But anyway, um, if they don't, shame on them. And also, this will be on their next test. Okay. So I'm glad you guys are back because that means we have the faithful. Um, okay. Thank you, Joanna. You are back too. Good. These are all the faithful students. Okay. Let me try to get this going here for us. We got the Poisson probability distribution formula. Okay. So I'm going to go let's go to our browser, I guess. Okay. So we're back at the browser. And here's what I'm talking about. Poisson. So in our browser, we do have some notes. I guess we should go back here. Let's go to our transition, right? Online transition. And if you take a look here, I got some more information. I'm going to put for you guys some examples here for binomial as well, like I put here. And you're going to talk about Poisson. So let's look at this worksheet for Poisson. Okay, here's a Poisson probability distribution. And this is our worksheet. And it's hard to see, but maybe here's what I'm going to do. I'm going to try this out. I'm going to be patient here. Okay. And we got more people back. All right, we got more people. So let me see if I can get this out. This is the past lecture for another class. And I'm going to try to recent. I'm not sure if it's recent. Nope. I want to open. Go to Files. Let's find the Poisson. Here we go. Poisson. So I'm going to open this particular document because I can actually control things a bit better here. So here's what's going on. We have another distribution. We have another formula that we're going to study. This one's called the Poisson probability distribution formula. It's named after a French mathematician, and it's really pronounced probably, I'm probably doing it wrong, but Poisson. Okay. I know. I've tried my best. Okay. I'm trying my best here. Poisson. The Poisson probability distribution formula. I know. Okay. So here's what's new for us. Here's what our random variable is going to do. Okay. If we read this here, X is the number of arrivals. So we're counting arrivals here. And we're counting arrivals in what we call an interval. So X is going to be the number of arrivals in some interval. We're going to talk about that. So a lot of things can arrive, ladies and gentlemen. So if I said to you, we could be sitting here, and what does it mean to arrive, right? Well, X is the number of arrivals in a particular interval. And this is arbitrary, by the way. But those are the two key phrases. So one example I can say to you, that the typical example I use is office hours. I can be sitting in any location now, whether it's in class, on campus, or whether it's here at home, right? Since we are at home. People who show up for office hours, I can think of as arrivals because you just arrived. So X could be simply the number of student visitors in an office hour. So I want to remark about that. Okay. Student visitors are arriving, and the interval is an office hour. So that's kind of a common example I like to use. Believe it or not, and I don't know if I want to go here, but maybe I will. We can also think of, as arrivals, earthquakes. You know, a lot of natural disasters we can think of as arriving. They can be hurricanes. It could be even a thunderstorm. We can consider those as arrivals. And how I can define that is I can say X is the number of, now I got to be specific. If I say earthquake, let's consider the big one. Now, the big one is an earthquake that's above, and I might be getting this wrong, but you got to consider what the definition is. An earthquake that's maybe at least 6.0 on the southern section of the San Andreas, right? On the Richter scale. And of course, it has to be on maybe the San Andreas. I don't know. You're going to have to ask your earth science instructors, what is the definition of, you know, the big one? And it could even be not even on the southern section. It could be just in California. Okay, you guys okay with that? So we can think of earthquakes. X is the number of big ones. And I wrote all over that. Let's go down here then. Quote unquote, big ones. And they can arrive in a year. So again, what's arriving here are earthquakes, and the interval here is a year. So these can all be thought of as modeled by a Poisson probability distribution or probability formula. So let's ask Catherine. I'm not quite sure. Is it an unexpected event? Okay. Yeah. Yes. Thank you, Catherine. It could be thought of as an unexpected event in some way, or I should say as random. These arrivals are not unexpected, but these arrivals are random. So that's a good thing to point out. I'm just starting to talk about the distribution. But yes, these arrivals, and let's put it up here in our notes, are random. Okay, random arrivals, and Catherine describes it as an unexpected event, sort of. I prefer just the phrase, it's actually thought of as independent arrivals. Okay, so the arrivals are independent of one another, random. And this could be modeled with a Poisson probability distribution formula. So there's a lot of different examples that we can consider here, which I wanted to get started on at least to lay the groundwork for your Poisson distribution. Here's another sort of idea, okay? Errors in a book. Believe it or not. You could be reading a book, or maybe you're an editor editing a book. You can have the number of errors on a page. So X can be the number of errors on a particular page, right? So I'm going to say X is the number of, and they're not just errors, there may be typos. Let's go with that. X is the number of typos in a book. And we should say, maybe specific, 300 pages. so that we can consider typos showing up. There's a typo, it just arrived. Okay, so it's kind of it's interesting in that way. So it's the number of typos that's arriving. And then our interval here is in a 300-page book. So this idea of arrivals and typos is actually very, very, it could be a little bit creative and arbitrary. And your book actually talks about another kind of idea. Your book says things like this. The number of hurricanes in a year. So we do have an example in our book that talks about hurricanes in a year. So we're looking at, hurricanes. So we can say a random variable, x is the number of hurricanes in a year. We can think of hurricanes even as arriving, and they arrive in an interval, we say, in a year. So those are the key ideas. Okay, now let me say something about these distributions here. If we go back and we look at our formula here, and that's not the one. Let's get rid of it. Let's look at word here. The key to working with these distributions is actually knowing this particular value, is knowing mu. Okay? Now, mu is the average number of arrivals in that particular interval, and that's what we have to take a look at and consider. And if we have that knowledge, we get to use this formula. And that's the idea. We're going to use that formula, okay? So this is the Poisson probability distribution. X is the number of arrivals. So X could be 0, X could be 1, X could be 2, X could be 3. And in theory, ladies and gentlemen, the number of arrivals can go to infinity. So this is a discrete random variable, and it's counting how many arrivals, what's showing up. Mu was the average number of arrivals. Now, this number is based on the past. So I want to say to you guys, this is based on past information. So in order to work with this distribution, you need the past, the average number of arrivals in the interval. Without the past, we can't predict the present or the future. This is a model. This is what we start with. It's kind of like the models that are using with this COVID-19 business and predicting all these things. They have to look at the past to get data. They get information. And from the past, they get to now predict the future or the present. So the past is never far behind. And ladies and gentlemen, the past is important. So let me write this down. For the Poisson probability formula, we need the past. We need the average number of arrivals in the interval. And if we have that information, we can use this formula. So P of x is mu to the x, e to the minus mu, over this x factorial. This is the Poisson probability distribution formula. All right, and we need mu. We need the past. So the example I typically go with here when I start this process, if you take a look here, we're going to look at office hour visits. We have Professor Snodgrass typically has 4 student visitors in an office hour, 60 minutes. Oh, and there's a typo. Hey, I wonder if I could fix that typo. Let me see. Can I fix this? Oh, let's see. Yeah. There, we fixed it. Snodgrass, I'm sorry, Snodgrass is spelled fine. All right, let's emphasize what we need. You see this number here? When they say you typically have 4 student visitors, ladies and gentlemen, mu here is 4. That's the past. Sometimes they'll say mean. That word typical can also mean mean, or they'll say average. All right. And so we now have that information, and then you say, well, what's the interval? In a 60-minute, in an office hour. So you get 4 student visits per office hour. Okay, that's good. This here is the past. That's past information. Okay? Now, look at the question. In a typical office hour, what's the probability? See question 1, you have no student visitors. Or remember, X is the number of student visitors, student arrivals. So if no one arrives, no one visits, X is 0. If one student arrives, question 2, X is 1. If 2 students arrive, we say X is 2. If 3 students arrive, we say X is 3. And if 4 students arrive, we say X is 4. So what we're going to do here, ladies and gentlemen, is we're going to use this information in our Poisson probability distribution formula to compute probabilities for arrivals. And so, of course, if you guys read on, I say to you, every time I use a formula, I write it down. It helps me to remember. And question 1 is X is 0, right? No student arrives. But remember, mu here is the value 4 because they're asking the question in a typical office hour, right? And so we get to plug everything in. So mu is 4 here, and there's another typo. And so anyway, I think what I'll do at this point, let's go back. Let's plug this in. I'll fix the typo. But anyway, mu is 4, and here's a 4. X in this first example, since they want to know, right? No, let's put that in black. No students arrive. That first question. So in this case here, X is 0. We know mu is 4. We just have to plug these things in. 0, 0, and 0. So we get P of 0 is 4 to the 0, e to the minus 4 over this 0 factorial. So I guess I want to talk a little bit about some of this and see what this means so you guys know. Algebraically speaking here, any base of the 0 power is 1. And then I'm going to say to you guys for now, take my word for it, 0 factorial is 1. I'm going to give you more information tomorrow about those factorials. But I want you guys to at first get started here with this idea to compute this. And we can find the probability of 0, no student arrivals, is really e to the minus 4. And this is what people ask. What is E? What is this number? Because it is a number. Now, those of you guys that have taken the prerequisites, right? All the prereqs. You say, what are the prereqs? Well, I mean, intermediate algebra. Math 125. Right? What was that? What is the value of E from intermediate algebra? Do you guys know what that is? It has a name. It's a special number. Okay? Let's see if you guys remember. E from intermediate algebra, the very famous E, is called, let's see, anybody know? The exponential number. And you might say, what's the exponential number? You guys remember the exponential number? E is approximately 2.718. So this is kind of why it's important to have some prereqs, right? To have some past knowledge, is because this should be now very familiar to us. And then simply to finish this question off, right? To finish this off so we can say, okay, we can brag to our friends. Let's approximate this to the nearest thousands here. Let's find what this is by the TI. So if I go to the TI, and let me find my trusty TI here. Let's clear all this stuff. The exponential number is down here. And I have to put E to the minus 4 power. Use the minus key, not subtraction. Exponential, E to the minus 4. And this is going to be, let's actually do the 10,000s here. 0, 1, 8, 3. 10,000s. Okay? So, ladies and gentlemen, this is how we compute using our calculator to the nearest 10,000s. But I already know what some of you guys are thinking. Some of you guys are thinking, okay, Mr. Judge, what about using that second distribution? I have a distribution list. I can use these, right? Well, yeah, you can if you have the TI. We just have to find Poisson, probability distribution function. Here's binomial, and sure enough, C. It says Poisson probability distribution function. Hit enter. Now, notice what it gives you. Now, I apologize for you guys. There is another symbol for the mean for Poisson. It's this lambda. This is another Greek letter. It means the mean. We know it's 4. Okay, we plug in a 4. So I want to remark, and let's put that in our notes. X is that same value. The number of arrivals, here it's 0. So the first value is the mean. The next value is 0. Paste this and double check. Isn't this the exact same answer? Okay. You guys okay with that? This is the same answer. So I wanted to show you, at least starting off today, how to at least compute this and introduce you to the Poisson with the remaining time that we had, because it's going to be what we start with next time. Okay, you guys? So anyway, this concludes our day. I'm going to put some examples for you on the website. Finish the binomial homework, and we'll continue tomorrow with the Poisson. Okay? So thank you guys very much for continuing the lecture. Okay? Thank you guys, and we'll see you tomorrow.